we will start with the most important speaker for the whole conference. And it's Teacher Wothers from Cambridge University. And I think I won't be long because we all want to hear you. So thank you.
I did wonder what I was going to be doing in this talk. But I must say, before I start, actually, how good it is to be invited here, and what a wonderful group of people, actually. I think it's one of the nicest conferences I've ever been to in terms of the people, but that's probably because we all share this same passion and the same interests, which is the interest for communicating science. So I think it's really quite noticeable anyway. But what I was going to talk about today was some of the projects that I've been involved with over the past, and some of the lessons perhaps to be learned from this. Actually, is it possible to put maybe the lights down on the front? Yeah, that'd be good. Some of the lessons that I've learned from this, and I think maybe I could summarise this with never work with children, lasers and Tesla coils, but you shall see why during this. But so some of the incidents that have happened. So I think one of the important things, for why I'm doing what I'm doing is because at a young age I was hooked on science. I suspect many of the people here it was the same thing. So I think then that the most important age group for me to try and attract into science are probably around the age of 8 or so. So you can get that little spark in them that then that they then carry forwards themselves for the rest of their lives. That's what happened with me. It was just finding out something about science. It's actually playing with magnets, and I still don't know how they work. I just thought, what fantastic things these are. But it's from an early age, and so the lectures that I do, many of the demonstration lectures are aimed at kids of about that age. But they're presented in such a way. There are lots of bangs and flashes, but there's a very strong educational message. But they're presented in a way that the adults in the audience, particularly the parents, will want to come along to these lectures, and they're actually secretly being educated as well. Because I think this is the other key thing. It's not only the 8-year-olds that we need to educate and get hooked on science, but it's the adults that really have a very bad understanding of a lot of the science issues, of course, and especially chemistry. And it's rather nice. I've had people coming up to me after some of my lectures and say, wow, I hated chemistry at school and couldn't do anything of it. These are people in their 40s, 50s or whatever, and say, suddenly I can see why it makes some sense, and how it's really, and I've learned more in your one lecture than I did in school, which I think is very nice. So I think people want to learn, but as I say, my lectures are generally aimed at a young audience, but the parents enjoy bringing their kids to these lectures, so they are quite fun. So anyway, so the different projects that I've been involved with. So first of all, this is it's a TV program for Discovery. So this is a few years now. So I'm looking not as fat in the things as you used to see. So it's quite a few years ago, but it's quite fun. So the idea was taking some really miserable kids, who had they were picked because they had no interest in science whatsoever. And the idea of the TV program was that they're going to be transformed and they're going to become geniuses after going through this program. So it's 6 one-hour episodes. But there's a few things that I wanted to point out about this. So anyway, so this is...
This is the big experiment.
Not Brainiac, right? It's not Brainiac, though. So, that explosion, by the way, that you saw, we went to a beach to do that, which was all quite fun. And so they had these, they were obviously experts. I mean, you wouldn't be doing that if you weren't. But there was a bit of a near miss when suddenly this thing blew up when nobody was sort of expecting it. And I think the producers were quite worried about this, that they could have killed all the kids. But anyway, right. So, first thing, I think the message here is, I don't know how many people have done work with TV, but it's, I don't really like it in many ways because they want to sort of steal your ideas, and because they can't do some of the things themselves, and then it's up to them how they present things. You have to be very careful. And then they tried to stitch me up. They tried to do something rather unpleasant at one point in this, pretending that for one of the episodes we took all the children into Soho, which is the red light district in London, to look at the neon lights, which is all very exciting. But then they had this surprise meeting that they set up with the headmaster sort of telling us off, which was completely ridiculous because, of course, there's no way we could have done this without the huge army of helpers and childminders that were with the kids at all times. And so it was, again, just sort of presenting things in a bad way. And an inaccurate way for TV, but we didn't allow that. They said that this is completely unacceptable. But anyway, here's another little illustration of this.
The protons and neutrons form the nucleus, which the electrons orbit. Peter has devised the practical, which he hopes will help the kids make a connection between the balls in front of them and atomic structure. It looks like a good start, as the cast seem to enjoy sticking Peter's protons and neutrons together.
Actually, amazingly enough, I think they're doing really well here. They're counting the number of protons, they're going up to the periodic table, they're writing down the right elements. I think it's, I'm very pleased. So this is, I mean, we were trying to teach the syllabus for the school through this, and so I thought, well, this is quite fun. So we had wooden spheres for protons and neutrons, and we arranged magnets on the protons and just essentially drawing pins on the neutrons. So they had to try and stick them together, and then they could read off the mass quite clearly on the balance. They had to work out which element it was from the number of protons, and then go to the periodic table and so on. So this is trying to give them something to do to begin to understand the idea of the structure of the atom, which was the first thing they needed to learn, really. But I mean, this actually worked quite well, this experiment, and the kids seemed to enjoy it. But the TV company then, kept the cameras rolling, so the kids are finished, and then they got really bored, and then they kept the cameras rolling. And so what they wanted to show, what their whole aim here was, without telling us, of course, was that they wanted this to be a failure, okay, and then the next thing to be a great success, okay. And so this was all completely sort of engineered without telling us that this is what they're going to do, trying to sabotage my experiment, which, as I say, I think on the whole worked pretty well. So what did they want to do instead? So they wanted the other co-presenter, Laura, who you'll see in a moment, to do a far more exciting experiment with the kids. Anyway, so this is her, which she didn't think of. I mean, this is from the TV company. They wanted this particular thing. So this is their view of how to teach the structure of the atom.
So there's one proton, that's a hydrogen atom.
Experiment.
We've got 2 protons and 2 neutrons. This is helium. Lithium. Right, one more red, please. Okay, that's beryllium. Boron. So we've got 6 protons and 6 neutrons. That's carbon. That's nitrogen. Oxygen. We're making fluorine. So we've got 10 protons and 10 neutrons. Neon.
It's the end.
So,
is it about PTSD?
Sorry, is it what?
Post-traumatic stress disorder.
So, it looks all very exciting and so on. But the kids were bored rigid for this. And I'll tell you why, because it took so long to film, okay? And again, for health and safety reasons, those motorbikes, you saw it was sped up on there, but they were actually crawling along, going so slowly that one of them even fell over. It's a great embarrassment of the big hairy bikers on it. But that wasn't the story that the TV people wanted to tell. They wanted boring thing in the classroom, get it out of the classroom, it's just so wild and wacky and so exciting. But and the way this was filmed, actually, they did it in reverse. So they started off with the lots of the kids. And then the poor guy at the end, he was absolutely just sort of so sick of it. He'd been there sort of an hour, waiting to film this thing. So it's, the message is, you sort of have to be careful with these TV companies and how they present things and so on. It's anyway, so it's quite fun. But I have another clip that this is quite nice.
And what element is in your balloon? Helium. Please do not set fire to anything apart from the balloon.
She's the real star of the show.
You
can't see her now,
But once
her name
Peter's
is Sadie
confident the kids
McCrone.
will behave, the fun really starts.
Now this one is dangerous, and it's very different from the helium. These balloons are hydrogen balloons. I'm going to show you now then why people do not fill their party balloons with hydrogen.
When it's mixed with air, hydrogen becomes incredibly volatile.
I didn't write that, you know, hydrogen doesn't become volatile. Yeah, exactly.
At last, Peter's got the kids' attention.
Yeah, exactly.
Even Sadie's fascinated.
These big exposures are getting me nervous, so I want to put some on my face. Boom!
So, anyway, yeah. No, I say Sadie on there, she was the real star of the entire show, I think. But she was quite unpleasant, I must say. At one point, she threatened to get her sister to beat me up. So we were giving a lecture, and this isn't, it sounds, okay, just laugh it off. But her sister had only just got out of prison for grievous bodily harm, so maybe there was something. But I mean, these kids, I mean, it's actually really sad. So the school here was an underachieving school, and it should have been a good experiment. But the problem was, I mean, all of these were picked from different classes, and they were the worst kids. That it doesn't matter what you did, they were not going to be interested in it. So there was, we had all these hovercrafts coming into the school, and they were driving and saying, "No, I'm going home and play on my Xbox in it." They just absolutely would not. They did not want to do it. But occasionally, there were moments when, there was a little spark there. And they did get really quite excited, which is quite good. But I think, again, to show you, how appreciative they were, there's quite a nice little experiment here. This is quite good. This involves some giant helium balloons. So the students had to work out how many giant helium balloons they would need in order to be able to fly, okay, which is quite cool. And then they did it in an experiment, okay, which is quite exciting.
In a challenge that has never been attempted before, the kids will have to work out how many giant helium balloons it will take to support their friend's weight. Too many will cause too much lift. Too few could have disastrous consequences.
It's good and high.
Okay, so that's all they had to do, and this is how it went.
Okay, Spurs, feel comfortable?
Yeah.
Yeah. Feel confident?
Yeah.
Assuming we went over the calculation, right?
No,
You double check. Failed student.
it's quite interesting. So there was no safety nets for them.
As the platforms rise
There's
ever
only
higher,
to stop
the
them floating
atmosphere
away.
in the Great Hall grows
Which is a bit of a shame, really.
When he's scared, he's quiet.
Oh, silly.
Shabazz will be the first to step off. And knowing how little some of his friends have paid attention in the past week, he's understandably nervous.
We're ready.
Oh, that's not.
The boys have got lucky. They guessed that 11 balloons would safely support the combined weight of Shabazz and his rig of 60 kilos. But in fact, the correct calculation is 12 balloons. As a result, Shabazz's descent is a lot quicker and steeper than it should have been. Seeing Shabazz drop so quickly has done nothing to calm Cherry's nerves.
Why is it shaking? Oh, stop moving. Just stay still.
Taking the next step will be the toughest decision of her life.
She's very young.
Drink for the ghost, chill.
girls' thorough calculations have paid off as Cherry floats slowly and safely to the ground. The relief of the rest of the class is obvious.
Okay, so there we go. All very exciting. Now the question is though, what do the kids think of this? Okay, and this is the important part of this. All right. So this is them interviewed afterwards, what they thought of the experiment.
I thought it was alright.
It wasn't exciting.
It wasn't really exciting
Because we weren't doing it.
Yeah, because we weren't really doing it.
It was absolutely boring. We waited all this time,
This is my
and all
favourite.
it did was flew with helium balloons on them.
That's my favourite quote. Yes. We waited all this time, and all they did was just fly with helium balloons. They're great. So, but I mean, the message here is because they weren't actually doing this. That it doesn't matter how exciting these things are. The kids really like to do the stuff themselves. And so, for the ones actually involved, it was quite fun. But for all these others who were just simply watching there, they were absolutely bored, of course. But that's again, not how they wanted to present it. So all that, all their classmates are really worried. No, they weren't worried at all. I mean, it was just in the script afterwards and how it's all presented. Anyway, so it was quite a fun series in some ways. But let's say there were other things that were less fun. But I think one of my favourite experiments was they were mixing up some. It was basically araldite, and they had to sort of work out the best proportions to mix the two ingredients, and then they glued one of their friends, and they were suspended quite high up near the Tower Bridge, which was quite fun, and then they dropped and so on. And that was quite exciting because one of them fainted at some point, so that's good. Yeah.
What did the kids actually learn from all this?
So they were doing calculations and things in the classroom. So they were actually doing
Basic
the
math
calculations.
for science?
Exactly. Yeah. So and the lift from the balloons and so on. So they did all this with smaller balloons earlier in the. So I haven't shown all that, but yeah. But they did actually have to take the normal national exam at the end of this, and they took it. I don't know. It was maybe 2 years earlier than they would normally do. And I mean, to be honest, so one of the girls on there, she got the top grade that she could, which was really, the highest grade possible, and that was actually quite an achievement. And so, yeah, I mean, there were some good things out of it, but it was all just, as I say, it's just what I didn't like was how it was manipulated by the producers and directors, really, behind the scenes, sort of thing, trying to portray it in a different way. But yeah. It was okay. I mean, so actually, I think really the kids were completely neutral, more or less all the way through. There were times when they were very, very excited and really enjoyed it, but on the whole, they were sort of pretty neutral. But the way it came across on TV, they were sort of not interested to start off with, and then really excited towards the end. But that was not necessarily quite how it was. But,
It's all about editing.
Sorry?
It's all about editing.
It's all in the editing, exactly. Yeah. Right. So. One of the other things that I'm involved with is the Cambridge Science Festival. This is, of course, the same sort of thing that you're all doing all around the world, sort of demonstration lectures. And I just wanted, there's just a couple of little clips from things that I wanted to show here.
I have over here a phosphorescent
I'm not
sheet.
going to finish this one.
Now, at the moment it's being protected from the light with a cover. So, the light's off, please.
So this is from a lecture about light,
Okay.
and we're going to do something similar after this talk anyway, so I won't play all
The
of
sheets here. Now, this is material that, when it's exposed to light, will glow in the dark. So if anyone with a laser pointer can please shine their light on this. Oh, very good. Some of them are nearly hitting it, yes. Very good.
Anyway, that's where I'm going to stop from this one, because as I say, we'll look at this one later. So in this is a lecture on light. I thought, wouldn't it be fun to give all the audience, they can have all responsible adults, they can have a little keyring laser. Oh, last time, never do that again. So this is one of my take-home messages: never give your audience lasers. So we were filming this thing, but there are lasers in my eyes and lasers on my groin, so I had to edit all that out. So don't do it, okay? It's not worth it. And actually, so one of the experiments that I wanted to do was to set off the finale and have a big explosion, but to do this they had to get their lasers and onto a target, and when a certain number of lasers were on the target, then it would set off this explosion. But actually, the thing we didn't realise, of course, is when you have so many laser dots, you have no idea which one's your laser dot, and so you can't do it. It's absolutely impossible. So it's quite fun, but very hard. You have to sort of get your laser, then you move it across, and you have to keep track of it and follow which one it is. Otherwise, you've got no chance at all. So it was a learning experience, I think, is the best way to put that. But sort of quite fun. But I won't be giving the audience lasers anymore. The next thing I wanted to show you is one from a lecture about air. I'll be wearing a very snazzy lab coat that somebody made for me. The different colours on it show the different proportions of the gases in the air. So the main body is nitrogen yellow, and then the sleeves, I think, are blue for the oxygen, and the pocket is the argon, which is red, and the bottom is the carbon dioxide. I know. So just in
I want
case
to look at the chemical properties of carbon dioxide, and one of the properties is that it's heavier than air. Now, I've got a bucket full of carbon dioxide here. I'm just going to pick up this bucket, being very careful not to spill any, and I'm going to pour some of this into the bucket here. Now, see if you can see what happens. Now, I'm pouring it now. Can you see it coming out? No. It's invisible. But look what's happening to the bucket. Okay, so that's because the carbon dioxide is heavier than air.
But the reason I wanted to show that is because it's such a simple experiment, and sometimes it's these really, really simple ones that can really get the kids excited. And so, I mean, it didn't quite pick up on the audio there, but they really loved this. There's a huge round of applause and cheering and so on. And I wasn't expecting that, because you just think, oh, it's just carbon dioxide, just heavier than air. But it's just the surprise in these young kids that it was really nice. So that was one of the demonstrations. But I think another one that I was really surprised at was explaining the Avogadro number during a lecture once. And so we did it in terms of, there's how many grains of rice are there in this bag, and then having a huge sack, and then how many sacks you need to give every person in the world, and then you need to take each grain and divide it, and so on. And so sort of gradually talking them through, trying to get them to understand how big this number is, because it's an impossibly large number that doesn't mean anything. But at the end of this, again, there's this sort of round of applause. And I felt really pleased that was one of the sort of nicest things, because it's just a number, and you're trying to explain this, and the fact that kids can get excited about this when it's presented in a nice way is quite fun. Right, anyway, so where are we going now? So I thought I'd say a few things about the Christmas lectures. So these are at the Royal Institution in London, and they were set up in 1825 by Michael Faraday. So here he is. So he was on our £20 note for a long period of time. And here he is lecturing in this very famous lecture theatre at the Royal Institution. So they happen once a year at Christmas time, so now the tradition is you do it once and that's it. So I was really pleased to be asked in 2012 to give a series of lectures. So you give three lectures, and they're televised. So it's quite fun. So this is the first time for a while that they've had chemistry. When they were asking me to write a proposal for this, they said they wanted on the elements. I thought, well, how are you going to do the elements in 3 lectures? How can you sort of split them up? So I was trying to think, well, what could I do? So in the end, I went with the theme of the Greek elements, which is a bit inconvenient because, of course, there were 4. And then sort of fitting the modern elements into that theme of air, earth and water, and fire being a common theme to all of the lectures, because there were lots of explosions and things. So that was quite fun. So I was going to talk about a few of the little demonstrations that we did there. So as I say, it's a great honour to be asked to do this. And in the past, apart from Michael Faraday and so on, and Bragg, Richard Dawkins has done it, Carl Sagan's given it, and so on. So it's quite a nice thing. I don't know if this is actually going to work. This is the intro that they gave for the day, which is quite nice. with this, I mean, it would have taken years to put together. In fact, it did, in a sense, take years, because many of the lectures that I've been giving for science festivals and so on, so they different themes and so on, and so it takes a long time to perfect these demonstrations, as you will all know. And so, a lot of this I had already prepared, in a sense, and so, but there were new things that we did as well. And it was quite fun because there were sort of excuses to try things that I've never normally done, and so this is one of them. This is one of the things that I was really pleased with, and it's an experiment I've always wanted to do, and this is to burn a diamond in air. And so if you look on YouTube, there's demonstrations of people doing it in liquid oxygen. I thought, well, I don't want to do it in liquid oxygen because kids aren't going to understand what liquid oxygen is. I mean, it's a weird thing. It's very cold, and it's sort of not something they will have come across. So I wanted to do it just in oxygen gas. So I designed this apparatus. So we have, there's a diamond on it. There's a close-up in a minute. There's a tube, oxygen flowing through this, just pure oxygen. So we had a little jet of hydrogen ignited by a sparker. So we have the oxygen flowing through, then turn on the hydrogen with it clicking, and then the thing lights. I was a bit worried because I managed to electrocute myself with this sparker, and my technician electrocuted himself. And then we thought to actually help out with the experiment, live as it were, during the lecture, we would get Sir Harry Kroto, who got the Nobel Prize, of course, for discovering Buckminster fullerene. So he was coming down to help out, and I was petrified that he was going to get electrocuted by this thing during it as well, and that'd be it, and then I would have killed the Nobel Prize-winning scientist. But fortunately, it was all okay. So we have the flame going onto the diamond itself. So this is a hydrogen flame. And the other thing I wanted to do, one of the reasons I've never done this before is because it was a real diamond. It was flawed, so it wasn't a high quality. It looked good to me. I mean, we'd had a little gag that was taken from his wife's engagement ring. So he brought down the ring and we prized the diamond out and put it into the thing, which is all quite fun. So then putting the hydrogen onto this, but I wanted to show, because this is the sort of classic thing that, with a carbon, diamond is made of carbon. So I wanted to show that, the product turns lime water milky. Okay, so this is all part of it, and which again you couldn't do if you were doing it easily with the liquid oxygen method. So this is why we were using the hydrogen flame playing onto it, so the only product there was water. But one of the things that I wasn't expecting, and this is a close-up, one of the things that I wasn't expecting when we were going through this and practicing with graphite and so on rather than diamonds, was that you can actually just switch the flame off and this thing will carry on, the reaction carries on. And so this is it, so there's no hydrogen flame on here. All that is a glowing diamond, and this is really very exciting. So there's no flames coming off of it, because of course this is not volatile in any way. And so all this diamond just sits there and it just glows like a little star. And it looks absolutely beautiful. It was really, really, really pleased. So nice piece of apparatus. So designed all this, and I was just over the moon when it actually worked. This is, I think, when I get excited about sort of science. And here is our lime water, and it did indeed go milky. And I thought, it was just so nice. So it's sort of a nice thing. So this is still, obviously available on YouTube and whatever. And so a lot of teachers use this, which is rather nice. One of the other experiments, I don't think I've got a picture of it, that I'd always wanted to do was in the periodic table. You have the most reactive metal, which is cesium. You see this in water. Well, that's easy. But then there's fluorine, the most reactive non-metal. And I thought, wow, surely everyone wants to see what happens when these two come together. So that was quite fun. So in the lecture on the water, when we were looking at the salts in water, we had cesium reacting with fluorine. So this was quite fun. So I had to go and find a fluorine specialist, because there's very, very few people. I mean, so even in our chemistry labs, and most chemistry labs, nobody ever uses fluorine itself. And it's very difficult to make. You have to have a special apparatus for doing this. Really horrid stuff. So I found a fluorine specialist. It was quite funny though, because I had never seen fluorine ever. He had never seen cesium, so this is quite exciting. So the two of us came together, me bringing my cesium, him with his fluorine, and we designed a nice piece of apparatus so we could again do this live in the lecture theatre, using fluorine and using cesium. So had a very thin tube filled with a little bit of fluorine and sort of blew that over the cesium, and then there was a reaction. It was quite fun, but it was a nice thing, and as far as I could tell, it hadn't really been done or at least recorded before, so that was quite exciting. So the Christmas lectures were giving me a chance to sort of try a few things that, just because they were quite so difficult, I would never be able to do them sort of lots of times. So it's sort of more of a one-off. And one of the other things that I always wanted to do, and so this gave me an excuse to do this, is to play with some gold bars, because they're just so exciting, having to pick up a gold bar. And so we wanted to balance a child with their weight in gold. And this was actually, so this was in the Earths lecture when we were looking at metals and ores and so on. But it was also ties in with bonding. So actually, I don't have a picture of it, which is a shame. We had a nice bonding machine that models how electrons help to bond atoms together, but then pull atoms apart. So it was all with pulleys and things. So you have sort of two atoms, as well, two big spheres that are moved together. As you put the electrons in, the electrons were heavy weights, and you put them in between, and they literally pull them together. But then there were a given number of slots to put these heavy electrons in, and after that they had to go outside, and then this pulled the atoms apart. And so actually it was, I thought, quite and it had a lot of technicians and teachers writing in to say, oh, what a fantastic model, and we will be using this, and where can I get one? So it really nicely showed how, I say, electrons can first of all help to hold atoms together, but then pull them apart. And so this is, we were gradually explaining why the bonds get stronger as you go across the periodic table, and then get weaker until, with the noble gases, there are no bonds at all between them. So this was a sort of a continuation of this. Why are certain metals quite so dense? Because, of course, we've got gold, we've got osmium in the centre of the transition metals, but then as you keep on going after that, the atoms are getting heavier, so an atom of lead is heavier than an atom of osmium. But then why is it then that the osmium is so much more dense? And of course it's because of the packing and how they're bonding, and that itself is to do with the number of electrons that are available to help stick the atoms together. And then as you keep on going, they're pulling each other apart until the bonds get weaker until you get to a gas again right at the end. So this is quite nice. So we were looking at why gold is quite so dense. And this idea of, it really is quite striking that, so we had these are real gold bars, we persuaded somebody to lend us the gold, which was very nice. But of course, they do this thing that, this is the correct way to store a gold bar. They have these cross-section, looking like that. But of course, most people in all the films, you see them the other way up. And then, that seems to be the natural way to put them, the other way up. And then you can't actually pick them up with one hand. So often, if the Bank of England is feeling quite lucky, it says, if you can pick it up, you can have it with one hand. And then you just can't do it because you can't get a grip on this. So this was quite fun. But so we had this big balance made, and they worked out how much gold was needed. And it was a bit of a fudge because we were a little bit of gold short. And so we had to ask the audience if anyone had some gold on them. And so this is how we introduced Harry Kroto when he puts his hand up and says, well, I've got this Nobel Prize here, would that do? And so, so we finished balancing off with a Nobel Prize, which was really corny, but it was so nice. But what was really fun, actually, because when I asked Harry Kroto if we could do this, if he could borrow his Nobel Prize and he could come on and help out, he'd lost it. So actually, because he'd put it somewhere safe in his house, and he's quite absent-minded, it has to be said, and he'd sort of put it somewhere safe and actually had lost it, and so he spent ages trying to find where he'd safely put his Nobel Prize. But anyway, so that was quite fun. But it was a nice demonstration. But so this meant that then I had this big balance, and we wanted to go around the UK, and actually we went to Japan and to Singapore with a version of the lecture series, which was quite nice. I still wanted to use this balance to show this incredible density of some of the metals. And so I actually had some tungsten blocks made that were the same dimensions as the gold bars here. And so they were quite expensive. It was a few £1,000s to have these things made. But the nice thing is that the audience can come up and pick these things up. And so this is the thing that really makes the connection with kids, when they can feel for themselves just how dense this thing is. So maybe you're familiar with Oliver Sacks' book Uncle Tungsten. And he says, the striking thing there was his uncle worked in a tungsten factory, and it made such a huge impression on him, picking up a relatively small block of tungsten, but it's just so dense, density of 18 point whatever, and it's just not something that you normally come across. And so, so we had these tungsten blocks made. They were quite expensive, but you can do the whole, can you pick it up with one hand, and they can't. And people and kids are really quite excited. Even the grumpy, miserable teenagers, they're going on. It's quite heavy, isn't it? So even the grumpy ones are sort of quite surprised by this, which is quite fun, which is nice. So we can't do it with gold all the time, but we can do pretty much exactly the same thing with tungsten. And of course, tungsten is even used to fake gold bars. So apparently, even in Fort Knox, they found gold bars with tungsten rods inserted into them because it has just about the same density. So it's one of the few things that you can actually use to forge a gold bar. So it's a nice model. Here are the gold bars there. And this was one of the other things. So yes, this is, as I say, never work with Tesla coils. I have to be careful when I say Tesla coil, because apparently one of my friends was up in the audience there, and there was this little old lady who says, why does he keep talking about his giant testicle? Ever since then now I'm paranoid and have to say Tesla coil. Yeah, anyway, so here's this giant thing. So when I was designing the lectures, I thought, okay, this is one of the things I want to do because it's just so awesome. Even though perhaps you could say this is more physics than chemistry, but what we're trying to show here, this is in the first lecture about the gases in the air, and we were looking at nitrogen and oxygen and so on, and different properties of them and different mixtures and so on. But this is one of the ways that you can actually get nitrogen to combine to react in nature when it reacts with oxygen during a thunderstorm. So we have this fantastic lightning, and the noise of this is absolutely incredible. And then you can smell, well, it's a mixture of nitrogen dioxide from the reactions that go on, and ozone, of course. But there is a noticeable smell there. But this thing, so I wanted to have this so it could lower down, like sort of Frankenstein style, coming down from the ceiling, which was great. So it came down, we had to do this. But the problem was, this thing really does have a mind of its own, this Tesla coil. So when we were practicing this, previously a few weeks before, all the alarms went off in the building. Oh, that's a bit strange. And then we found out that the alarm was actually in the basement, so we thought, okay, clearly it's not us. But then it started controlling the guy's phone, who was filming it on his camera phone. It started sort of doing weird things and resetting everything. And so then during another rehearsal, during the day, again the alarm went off. And we were not popular then because there was a very important meeting taking place and the whole building had to get evacuated. And it was still apparently registering in the basement. And so then we thought, well, maybe it is us then, since this is two in a row. And all of the lights in the lecture theatre kept flashing and they couldn't switch it off. It was amazing. And so we've taken this to different locations around the UK, and everywhere we go, it does something different. Okay, it's really cool. So we gave it in a school. They had this huge sort of Victorian stage, which was fantastic. They had this fantastic clock, and it just stopped the clock. And it never worked again. So that was fantastic. So they remember when we went there, which is good. And in other places, it switch lights on and whatever. And they say we can't switch them off now, and so it's great. So the difficulties it caused. So when we were filming this, so there are these little cameras on here. These were looking at the audience, and the audience were holding up periodic table cards and forming a periodic table, which was all quite fun. But so it shut these cameras down. They just went and just shut down like this as soon as you switched it on. And the camera crew were absolutely petrified. They were so in the end, it was almost touch and go whether we were going to be able to do this, which I really want to do because it is absolutely awesome. The noise it makes, and it's really exciting. And to have these huge sparks coming down in the audience, which was great. But it nearly didn't happen, and this was because the Royal Institution would not take responsibility for this. They were paranoid, and somebody had a pacemaker, they were going to die. They were paranoid that all of the £1 million worth of camera equipment that was being used to film all of this was going to get destroyed. And so in the end, it was very brave of the owner of the production company. He said, well, we've got to do this, and we're just going to do it, and so that's it. So he took personal responsibility for this, which was quite remarkable. And it was more or less fine on the night. So they took most of the cameras away that were not absolutely crucial, and they had the other cameras on it. But still, there's a chap in the 2 floors up who was editing this. He was sort of more or less editing it as it goes along, because there's a very short turnaround time. But apparently, during using this, it suddenly changed all of his equipment, changed the language into Polish for some reason. So it really is, it really does have quite a mind of its own, which is quite fun. So, and you never quite know what it's going to do. But it sort of, it was great and it all worked and it didn't destroy anything irreversibly. So, apart from the lights and the lecture theatre, which they had to fix afterwards. But anyway, so it was good. Where are we? So yeah, these are some of the cards that I was talking about in the audience. And this was a rather unfortunate picture. So we were talking about radioactive decay. Okay? So this is all very, very innocent. So we were talking about how, so one atom, the nucleus loses it's an alpha particle and it moves 2 spaces along. And so, so we're going from radon there to polonium, then going on to lead. And so the photographer just caught this picture of these kids spelling out porn, but there we go. With Mrs. Proto not looking very impressed with this. But, anyway, so it was quite fun. It was yeah. Anyway, so where are we? So this is I say one of the other things that I'm involved with. Then something that actually, probably the reason that I'm here, with working with other people here is through the Chemistry Olympiad. And I thought I'd say a few things about this, since it's part of what I do. So this is, for those of you that don't know, takes place in most of all the sciences, so physics, maths, chemistry, biology, astronomy, informatics, all sorts of things. But I think that it's a really, really worthwhile thing. So this is when we had it in the UK. So I think it's closer to getting on to 80 countries now for chemistry, but more in physics and more in maths, and even more in maths, which has been going the longest, I think. So this is, I think, it's a very worthwhile thing. So for those of you that don't know, in this, certainly for chemistry, these poor students, well, the students are selected through a national competition, so they have their own written papers within their home countries, and they select the students to participate, a team of 4, and they're competing individually rather than with teams. And so they go abroad, they have 10 days, which is great for the kids, so very sort of social things, they get to sort of see the country that they're visiting. But they'd have a 5-hour theory paper and a 5-hour practical paper, so they actually have to do a practical exam, which is all quite fun. So the mentors that are accompanying them, I say we're some of us are mentors in the Olympiad, they have to do all the work, so translating it. So this is not an exam that's taken in English, it's taken in their own languages, because it's only on their ability to do the subject, the science or whatever, which is very good. And of course, it's a great chance for the students to go and do lots of social things. So here they are going out and doing fun things with a castle and so on, and coming back and get absolutely exhausted at the end of the day. This is one of our teams before. So I was going to say a little bit about the UK side of things. So why I think these are really important, these competitions, is it's another way to get kids excited about chemistry. So the demonstration lectures are fine, and I think they're very good for particularly young kids getting that little spark there. But then, the question is, well, what do you do for these older kids? Yes, they can enjoy demonstration lectures and so on. But unfortunately, the exams that they have to sit in the UK, at least, the A-levels, they're not very exciting. And the chemistry ones certainly are not particularly challenging in many ways for the really good students. And so, it's certainly felt that some of the better students will tend to pick other subjects because they don't think chemistry was particularly hard or interesting or whatever. And so what we're trying to do in our national competition, yes, there's this small aim of trying to find the 4 students to represent the UK, but really we're trying to promote chemistry in the country, even for kids that are not going to be in the top few at all. So we try to do things that are a little bit more interesting in the first paper. And this goes round, there's about sort of 6,000 or 7,000 students sitting the exam, so we try to do questions that are sort of relevant. So this one was looking about the space shuttle and the fuel, the solid rocket boosters that use aluminium and ammonium chlorate, and then there's hydrogen and oxygen in the main tank and so on. What else have we got? This one was looking at pollution in the Taj Mahal and looking how it's dissolving it and so on, and what we do to prevent it. Catalytic converters, and how they work. And this was a diesel one actually, which is quite exciting. In diesel catalytic converters, they have a lot of particulates, and they over-oxidize it, so they have a lot of nitrogen oxides left over, and so then this is used, ammonia is used to reduce it back down again. So it's a lot of sort of interesting chemistry, but put in a context that they can relate to. This is quite fun. This was we were looking at when the oxygen masks come down on planes. They don't use cylinders of oxygen gas, it's chemically generated. So this is from the decomposition of sodium chlorate, and having particles of iron in there, and it's an exothermic reaction that keeps it going. So this was looking at the chemistry and how much you need and so on, and so we found all the data out and so on, which was all quite fun. So, but the interesting thing was trying to word it in a nice way that you're saying that how much oxygen do you need before your plane reaches a nice safe altitude. So this is what it was doing here, and so they were looking at that, which is all quite clever. This was why your urine smells if you eat asparagus. I'm sure you've noticed, but it's the chemistry involved with that. And this is going back to the original papers and trying to find out and so on. So it's all sort of interesting things. This was a nice question that a lot of teachers come back to me and say, oh, they really, really like this. This was a molecule that was made a few years ago by James Torr in the States. So he sent us a sample of this, which was very nice, and we run a 700 megahertz proton NMR spectrum. And the kids can actually, we picked this particular molecule because of the symmetry in it. It's actually relatively easy to understand the carbon NMR spectrum and then the proton NMR spectrum, and the kids can just about sort of work it out, which is quite nice. So, but we needed a really nice high-res one to be able to do this. The same group, so he made all these molecules just because they look like little people, which is amazing how he managed to get a grant for it, but there we go. But it made a lot of publicity from it, which is quite exciting. He also did these ones. This is this nano car, and now this is actually quite clever because this has wheels that only turn in one direction, and they're driven by light. Which is quite exciting. So there's a mechanism here that this can only turn in one particular direction, and it's due to a sort of a bond isomerism there. But again, it was quite fun getting the kids to work out, which way this car goes, depending on the wheels, how they're attached, and so on, or whatever. So no, it was quite fun. This is a question that was about supernova. So the NASA website is, of course, absolutely fantastic, as I'm sure you will all be using. All the images you can use, as long as you just say that they're from NASA, and so you can find all sorts of fantastic things there. This is, again, it's something that you can get the kids to do for themselves. They can work out what element is in this supernova just from the frequency of the light that's coming back to Earth. And this is because they're one-electron systems, so incredibly simple maths. So this in astronomy speak is oxygen 7+, so just one remaining electron, and neon 9+. But I say from the wavelengths themselves, they can work out what the transitions are and so on. So that's quite nice. What else? This was in the news. So what we're trying to do here, these are questions that are sort of in the news, and sort of quite exciting things, but trying to translate this science from the papers themselves will be utterly inaccessible to the students. And so the job here is to try and translate this into something that they can do for themselves. And this was one that I was particularly pleased about. This was a Dutch team who were looking at this Van Gogh painting, if that's the right way to say it. I should ask. Yes, we're getting some nods, that's good. So this is called a patch of grass. And hidden under this painting is this old lady, so she's not normally visible like that, of course. And they're using this technique, looking at the particular wavelengths of the radiation coming off to work out not only what elements there are, but also what oxidation state these elements are in. And so this means that they can actually work out what the pigments are, because they're sort of pretty well-known pigments. So for instance, the lips here, this is from cinnabar, from mercury sulfide. So because they're detecting mercury and sulfur in that region, then they know that it's mercury sulfide, and they know that it's this red pigment. So they can actually get this huge detail of even the pigments that were used underneath this grass. So it's quite exciting. But I say, getting this into a state where the students themselves can actually do this and calculate these things is pretty good. All of these questions, by the way, are available on the Royal Society of Chemistry website. So all the questions are there if anyone's interested in these papers. This is, we told them how to synthesize rohypnol, which is a little bit controversial perhaps, but the kids, the exciting thing is that the kids come out of this going, I can't believe that they told us how to make rohypnol. I mean, there's no way they could make this drug, because the synthesis is actually technically very hard, and they wouldn't be able to get the ingredients, including cyanide, for instance. But the fact that they're excited enough to talk about it afterwards to their mates is quite exciting, I think. This was a really interesting thing, actually. This was a drug a few years ago that was going to solve all problems of obesity and addiction. So apparently if you have this, you stop wanting to drink too much alcohol, you stop wanting to smoke, stop wanting to eat. But apparently it was then withdrawn because you just stopped wanting to live. And so there was an increased rise of suicide, apparently, on people that are taking it. So it came and went, this drug. But anyway, so it was quite nice at the time when we were looking at the synthesis. This was synthesis of Viagra. Again, another one that the kids were very excited about. But there's no picture because we couldn't get a picture, actually. We asked Pfizer, can we have a photograph put on here of maybe the pills? They said, well, no, can't do that. We can't be encouraging its use in a non-medical way and all this sort of stuff. So in the end, I thought, okay, we'll just put censored on it. So that's why that was Tamiflu. So again, in the news for bird flu, and this is the synthesis of this. So it's quite a tricky synthesis, but again, can be presented in a way that the students can understand. Lipitor, the biggest selling drug in the world, that was quite fun. So that's so some of the things from the Chemistry Olympiad. And finally, what I was going to say a few words about was this other thing we set up, the Cambridge Chemistry Challenge, because there's a few interesting ideas from here. This is in two parts. One is a written paper that the students sit in their exams, and this is the year, well, before they decide what they want to do at university. And so the Olympiad in the UK is certainly generally taken by students in their final year. They've already chosen what they want to do at university. This one is a year before. So we wanted to do something similar, so have some interesting questions, but they need to be at a lower level that the students can tackle. So again, we're trying to get some interesting things that maybe are in the news. So this was from the 2013 paper. This was just discovered this oldest sample of water, which is all quite exciting, discovered in Canada. This was, so the students managed to work out how old this is, to actually do the calculation themselves. And it's actually quite complicated. They spent a long time going through the paper with this and actually again contacting the original author, and he was trying to work it out with me because he was having problems as well. But eventually we managed to get this into a form that the students could understand. And it was exciting because bacteria thought to sort of be able to might be present in this water that's 2.4 million years old, or is it billion or whatever? Yeah, whatever. Very old, yes. So quite old. So this was on last year's paper. We're looking at the James Webb Telescope. Of course, this is using beryllium here, because it's very hard and low thermal expansion or something like this. So it's which is why it's used very light, the lightest metal that you can have up there safely. So they were doing some simple calculations with this. And this, does anyone know what this is from? Oh, I thought this audience would know. So this is from the film Galaxy Quest. I don't know if you've seen this. So this is what power. So this Galaxy Quest is a fantastic film that I can recommend to you. It's a sort of a gentle, respectful play on Star Trek, but it's about these aliens that are receiving the TV signals from this TV sci-fi program called Galaxy Quest, and the aliens build a replica of the spaceship that actually works, and so they make everything actually work, and it's all very exciting. But their ship is powered by a beryllium sphere, so this is what this thing is. But of course, as I'm sure you will know what Star Trek uses. Did you know what Star Trek uses to power their spaceships? Oh, well, maybe, I don't know. But I thought they used dilithium crystals, exactly. And so the interesting thing is dilithium crystals. You can't get dilithium crystals, but you can get dilithium. And so one of the things that we were looking at the end of this question was the bonding in the dilithium crystals, and then why you can't get beryllium-2 molecules. You can get Li2 molecules, but you can't, well, they're very, very incredibly weak bonding. And again, this is this anti-bonding effect of the electrons there, which is quite exciting. So it's sort of beginning to get quite tricky chemistry, but it's presented in a way that can be understood. This was from 2013. This was, you may remember, in the UK at least, we were paranoid about eating horse meat because it had been detected in minute quantities in things like beef burgers and beef lasagna and so on. There were traces of horse meat. And so the worry was, because this drug was used for anti-inflammatory in horses, and it used to be used in humans, but it's been banned, and so there's this, unsafe for humans, and the fact that it's got this drug in. So they were looking at the synthesis of this and looking at how to detect this, and of course, again, the media throws this out of all proportion. So we thought, well, okay, we'll do a calculation. How many burgers, so these were the correct levels that have been detected, how many burgers would you need to eat in order to get the medicinal dose of this compound when it was used in medicine? And it came out to be 250,000 burgers, in one go. So this is never mentioned in the media, of course. They never. It's just all scaremongering from chemistry. So there's a sort of serious message there. One of the other ones we did was on homeopathy a few years earlier, and they had to work out how much of this homeopathic remedy, an arsenic remedy, they would need to drink in order to have a lethal dose of arsenic. And they had to express their answer in volumes of the earth, and it came out to be something like 2,000 times the volume of the earth in order to have a lethal dose.
Has memory.
Exactly, it has memory. Well, then they had to work out how many bottles you'd need to drink in order to have a 50-50 chance of having one atom. And again, it's millions of bottles of the stuff. It's just all nonsense. Yes, so it's a good job it has memory. Yes. Anyway, yes, this on the top here. So this, when this compound phenylbutazone is metabolized in the body, it's converted into this more soluble form, oxyphenbutazone. But this is a good top tip for you. This is the highest possible word score in Scrabble. Okay, so on I think it's on Wikipedia or somewhere, there is a link to this to show how it can be played. Now there's a few strange words in this. That's Wakeners. I have to keep misreading that every time I see this. But so down the side here, so they've got all this has been set up, and they're showing right from the beginning how you can end up doing this. And so this is your hand. So these are the letters that you've got. You think, well, what can I do with this? And there we go. So down here, oxyphenbutazone just fits in. And it all fits in perfectly, and it scores something like a couple of thousand points in Scrabble. So there's a top tip for you there. If you ever can spell that, you're going to win, basically. Yes. But there we go.
All the words.
Yeah, exactly. This is the thing. So I don't know what was going on here, why they had to have that, but there we go. This is interesting. So the paper that we're sitting here, so that we set for our year 12 students, so let's say one more year at school to go, it's a challenging paper. So the students find it really difficult because it's not in the same format as their national exams that they have to do. So the questions are different. So in their A-levels, so students, I've had students come to Cambridge and say that they found it really stressful at Cambridge because whereas at school he would go into the exam and know that he'd basically done all of these questions before. Maybe there's tiny little variations, but he'd seen every type of question that they could possibly ask. But when you get to university, as we all know, the questions are not like that, and it is, you have to begin to think for yourselves. So this is what we're trying to encourage in these papers. And we make them difficult. They are challenging, but they are actually doable. So the teacher can take them through them later, but they do find it a real challenge because it's not in the same sort of format. And so actually the sort of the modal mark here comes out to be around sort of 14, 15 out of 60. Okay. So, and we get feedback saying, oh, my students are all going to get the top grades in their national exams, in their A-levels, and yet they're only scoring marks around here. And we say, well, look, these are the skills that you really need to try to, that they can do this. There's nothing in this paper that the students are not able to do. It's because they can't see how to do this yet, and this is the sort of thing that you should be encouraging. So this is, I say, it's for sort of older students just before they're getting to university, but it's something to keep them engaged, show that science is relevant, but also that it's can be an interesting challenge as well. But the top students, as you see up here, are getting almost full marks. For those of you that aren't chemists, I shall point out that in group 11 of the periodic table, there's copper at the top, there's silver at the bottom, and then there's gold underneath that, and then underneath that is one of the newer elements that's only been discovered relatively recently, and just a few atoms, and this is the element runtgenium. So these are our top awards, and these ones here we invite to a training camp in Cambridge for a few days, a residential camp, and that's really great fun. So we've got all these really bright kids, and they can do some demonstration practicals and lectures and so on, so they seem to enjoy that. And so this is feedback from one of the teachers. They're just sort of saying that they really appreciate this, having just another resource. And again, all of this is available on the website. All of these questions are there, and anyone can steal any of them, use them, whatever you want to do with them if you want them. So that's quite a nice thing.
Which website?
So it's, well, you can search for the Cambridge Chemistry Challenge, or the website is C3L6.com. So this is the Cambridge Chemistry Challenge, that's the C3 bit, and the L6 is the year at school that we primarily aim it at, which is the lower 6th. We liked it because it looked like a chemical formula. But, C3L6.com. So that's one side of this competition, the written paper, trying to get something interesting but challenging. But then the other thing that we set up, this was a web-based competition that students all around the world can participate in. And the idea here is what we wanted to try to do was to find those students out there that have this passion, for them to be able to identify themselves to us. And so, well, I mean, it was initially quite successful when it started off a few years ago. Numbers participating have died down a bit. I mean, it's a few hundred every month. But we put 5 questions online on 1 second past midnight on the 1st of the month. And the idea is that these have to be questions that they can solve using the internet, because of course, all kids are just going to instantly look up the answer on the internet, but they have to be Google-proof questions, so you can't literally type in the question into Google and get the answer. So, I mean, this is this is the synthesis of runtgenium, as it turns out, from the Russian scientist here. But so these are some of the different questions that have been used. So this is all they will see. Okay, and so they have to work out what the question's about and try and find out the answer. So this was, this is the Big Bang, but this is how much energy you can get from the binding energy when 4 alpha particles, 4 helium nuclei are forming oxygen-16, how much energy is released. This is Falls gold iron pyrites. They had to identify. This is looking at phenolphthalein, which is an indicator used in chemistry, colourless in dilute acid. This beautiful pink colour, which they recognise, but they might not know that it goes this beautiful orange in very strong acid, which is quite interesting. This is Boltzmann's tomb, his equation there, so this is where he's buried. This was looking at these porphyrins, so these are present in blood with an iron atom in the middle, in chlorophyll with a magnesium atom, and in the pigment in there with a copper atom, so they had to identify the elements there. So these are some of the students who have entered from all different countries, all around the world. So it's quite fun. Though if they do, as soon as they've solved the 5 questions, they move from one question to the next question. They're getting so harder each time, and when they finish them, their name can appear on this honours board. So it's a competition to see who can solve the 5 questions the quickest. And it always seems to be the same chap from Bangladesh who seems to win, which is very nice. I mean, it's great. I've been in contact with him, and he's just so excited about chemistry. But unfortunately, it's really quite sad because his parents didn't let him do the science that he wanted to do. He had to go into a different area and so on. But he's got this real passion for chemistry. He's something he's always wanted to do it. So it's quite nice to get people from all around the world with this. So these, the prizes, and I was going to pass these around, these are quite cool. So these are something that we had made. So these are nice little, the crystals. When you get things like the Eiffel Tower engraved with a laser, I'll pass these around. But what they actually are, these are atomic orbitals. So these show the electron distribution function of a hydrogen atom in various excited states. So I've never seen these in a 3D version. So when I saw a little Eiffel Tower in one of these crystals, I thought, oh, this is exciting. Maybe we could do electron distribution functions. And so we did all the calculations, sent them off to this company that makes them. they thought, what the hell is this? It's just a load of dots. And then we've had loads of these made. We send them to every school that participates. And again, I mean, the teachers are saying, wow, this is a really fantastic teaching aid. So that they like these. And these are also the prizes that the students get. So here they are all around the world with their precious orbital like that. And so this is one that we give to some of the other winners. And there we go, and that's pretty much all I wanted to say. But I have a demonstration. So, I mean, the thing about my demonstration lectures, there's a lot of demonstrations in them. And actually, with chemistry, I mean, it takes quite a long time to set up. So, we came here just after 8 this morning and only just had time to set up one demonstration. But it's quite a fun little thing. So we're going to try this in a moment. I don't know when it's going to work. It might not work. It's sometimes a bit temperamental, so we shall see. But so this is from a lecture that I give on light, and I also have, if anyone is interested, somewhere or other, a load of DVDs from some of the different lectures. So if anyone wants to take any of those, feel free. I'll just leave them there. So there's a number of different lectures that I give on. There's a strong theme throughout all of these things. But this demonstration I'm going to do is from the lecture on light. Okay. And this is where it was touched on in the lecture that you saw earlier. And so I need some volunteers. Actually, I need a very tall volunteer. Kuba.
Okay.
Kuba is a very tall volunteer. Good. And I need a shorter volunteer. Shorter. Okay, so somebody else. Okay, good. Yeah. And so I need. So is there anyone shorter still? You'll be fine. Is there anyone shorter, even shorter? Okay. Yes. Yeah, good. Yes, that's good. Yeah. Good. And we need one. So we need to arrange yourself in terms of height. Okay. So watch out for the wires.
Which way?
Well, it doesn't matter. However you want. Okay. Now we need somebody in between. I think we need a girl for this as well.
Between 1.75 and...
Yeah. So somewhere in between here.
170.
Okay. Okay.
Oh, girl.
Oh, well, no, never mind. Did you volunteer? Yes. Yeah. Okay. Right. Well, sorry, you've been replaced.
I've been replaced.
Sorry.
Right. Good. Okay. Now, so I mean, this is just about a bit of fun. So I normally do this with the kids, of course. And what this is about, I mean, it's looking at the wavelengths of light and the energies of light and different colours, different energies and so on. So we have different coloured lasers here. So where are we? We need... the longest wavelength, so you get a red laser. Don't look at... See, this is what everyone does. They put it in their eyes. It doesn't matter exactly. You tell them this, and the first thing they do is, it's not working. You have yellow. Okay, very good. You have green, okay, and you have violet, okay. So just test them for me on the floor. Lovely, marvellous, right. And so over here, I have. So this is what we were doing in the lecture with basically some phosphorescent sheet, and I normally do this on a big one or have somebody come up. So first of all, if we have the red laser on this, okay, all over, yeah. So nothing happens, okay. Right, okay, let's try yellow. So we're increasing the energy, of course, and this is what you'll be talking about and showing relevant slides and so on. Nothing there. Okay, let's try green. Nothing there. And then finally, the violet one. Wow. Okay, and this is quite nice. So it's not because the laser is higher power, because of course there's plenty of demonstrations when it's just because it's a high power laser. It doesn't matter what colour it is that it'll burst thing. That is quite nice because you can show complementary colours and so on and all those sorts of things. But I mean, what we're trying to show here is that there's an increase in the energy of the photons with colour, okay? And that it goes, the longest wavelength is of course the lowest energy, so this is quite fun. So when you get a really little kid out, he's very excited that he's the powerful one with the laser that can do the exciting things. Okay, so now we've established then that this one has the highest energy. We're going to try another experiment, and I think it might be good for people sitting here just to clear over that way, just stand over there for a moment, because you might get hit by something if it works. Okay? It comes out quite fast, right? So this is actually I'll move my laptop as well, I think. Right. Okay, so make yeah. Okay, it might be quite painful if you're hit, okay? No problem, okay, right. So, this is a mixture of hydrogen and chlorine, okay? And I'm trying to aim this approximately as a... You're probably in the most dangerous position, but yeah. So I hope that this will go. Well, you know, you never know. Right. There we are. Yeah. Right. Okay. So the tube here.
That's back over there is going to go.
You reckon? Right. So the tube here is filled with a mixture of hydrogen and chlorine. Okay. And so what we're going to do is going to try the different lasers in order on this. Okay. So this is actually a silica tube, and so we're using silica because it's not going to be absorbing so much of the light. So if we come over this way, all the lasers. We're going to start off first of all with our red. So if you come here, this way.
Okay.
Yeah, you do it from here. Okay. So and now there's a little window in the middle there. Okay. So you have to aim your laser on the little window. This may work, it may not work. You know, no idea. Okay, it depends because it's been a while. It's been sitting there for some time. Okay. That's probably not going to work. Okay, let's go to next energy. So this is yellow. Very nicely lasered, but no good. Okay, go to green. And let's try the violet one. Fingers crossed.
Violet?
Violent.
Maybe go a bit closer. Try a bit closer. I think it might be tricky because if it hasn't gone
Without
down.
expression over there.
Yeah, it's. I do have a spare one, which I might get out of. A mixture of hydrogen and chlorine. So, let me give you a little nasty. A mixture of hydrogen and chlorine. And the reaction taking place there, I mean, the blue light, the violet light, has enough energy to separate the chlorine atoms in the molecules. And that then starts a chain reaction. So, but it's only the blue light that is able to do this. Again, it's not the power of the laser, it's the energy of the photons. So, and one of the nice things is when I first gave the light lecture, and this was maybe about 10 years ago, I had the only blue laser pen in the UK at the time, and it cost several £100s. But this laser here is now, I think you can buy them for £3. This is because these are the ones that are used in Blu-ray DVDs. So really, really cheap. But it makes a nice, striking demonstration of the energies of light, I think. So anyway, there we go. That's my
If you have any questions, yeah. Sure. Sorry.
What kind of paper is this?
So this is the same sort of thing you can buy. This is phosphorescent paper. So because it's giving out a nice green light, you need to have higher energy than green in order to get it to fluoresce. So yeah, you can. I mean, I have reels and reels of this, so lots of it. You can buy it quite nicely. It's actually. What is it? Strontium aluminate, yttrium-based strontium. No, europium-doped strontium aluminate. That's what the active pigment is there.
And you can get this.
Well, I mean, I contacted the manufacturers for this because they gave me, meters of it, which is great. Because then you can get the kids to sort of pose on against a sheet of it, and then shine a nice bright light, and then they get their picture on it. It's really nice. And actually,
a normal flash will work.
Yeah, we can use well, you need to check in advance which sort of light bulbs you're going to use. I mean, it needs to have sufficient energy.
White LEDs are perfect for that.
Yeah, some of them work, some of them not so good, but yeah, but it's quite nice. And one of the experiments that actually we did with the grumpy kids that were never excited by anything. But one experiment that really got them very excited. We have a huge room with all this sheet of paper going all the way around, and we used it was a magnesium flash. So it was the sort of thing that you use in photography. They used to use, Victorian times. we walked, so this was done in a theatre in London, and we said, it's going to make some smoke, and they go, oh, no problem, we can do this. And I said, no, it's going to make a lot of smoke, Anyway, so we did this, and there was tons and tons of smoke, and the alarms went off, and they come back and say, what have you done? What did you do? Anyway, but it's quite exciting, the smoke billowing out of the doors. But the kids were really, really excited, because they had this, and they were all doing these poses all the way around, all the class, and that was one of the few things that they came out afterwards and said, wow, that's the best thing we've ever done. So that was quite nice. So it was nice to get a good reaction at some point from them. Any other questions about anything?
Peter?
Yeah.
You're a poster.
Oh, yes, thank you, yes. Actually, yeah, I'll show you this. Could I have the lights up for a second? So this, the lights at the back, or these lights or whatever, so you can see. So this poster, actually, yeah, thank you for pointing that out.
No.
So this is to advertise...
On. No, off. Off.
On. We'll have it on. Okay.
You said off at first.
Did I? Okay, right. Okie dokie. So, maps. So this is, so we sent this to every school in the UK, and so it's about the flame test. So this is something the kids need to know. But we wanted to do a poster that was advertising our competition, but was going to stay on the walls, okay? And so, okay, I mean, it's quite a nice poster, and it shows, we actually made these, so these are not fake things, these are real flames. And so they're soaked in the salts of the particular elements, and then we actually videoed the flames themselves. But the fun thing is, it uses an app here where they come alive. And so it's quite good. Sorry, press the wrong button. Yeah, exactly. So is it still on? Yes. So I can have my hand here, and you can see the handle there. But and then you can tap on them and get a bit more information. And it starts speaking to you, like it's turning up. So, and it's showing their line spectrum and so on. So they can do this on their apps, on their phones and so on. And what's nice, I mean, so when we sent these out, teachers were writing back saying, wow, the kids are so excited by this, they're all blocking the corridors looking at this poster. And we still get in requests. So this was several years ago we did this, and people are still saying, our poster's worn out now because we take it from room to use in the classroom and so on. But so that they ask, can you send us more copies? And so we're still sending these out. Well, almost every week we send out one to school somewhere, which is quite nice. But again, it's just a little bit of fun, on something that would otherwise be a little bit boring. But these apps are quite clever things. So this was a collaboration with somebody from the engineering department at our university that was working on this augmented reality. So it's quite nice. So thank you for pointing that out. I have some of these places if anyone wants to take them home. If anyone wants a poster, I have a few here. If anyone wants to take one. But there's not that many. But there's that one there.